So in this recording, we will be talking about performance evaluation. So when we evaluate forecasting models, it's kind of attracting to pick the one that performs best on the data we already have. But if we use the same data set to both build and test the model, we introduce something called bias. So the model might look good for two reasons. Either it's genuinely a better model, or it's simply taking advantage of chance patterns in the data. And this leads to what we call overfitting. Overfitting happens when the model captures not only the true patterns, but also the random noise. And that makes it look strong on the current data, but weak on the new data. So to visualize this, maybe you can think about like a tailor that making a suit to someone's exact body measurements. It will fit perfectly now, but as the body naturally change over the time, the suit will not fit anymore, right? In the same way, the overfitted model performs poorly when applied to new dataset. So to handle this issue of the overfitting, one of the most important steps before applying forecasting methods is called data partitioning. And this means we split the data into different parts, and as we did in the data mining classes, we use one part to build the model, and then we test the model on the other part to see how well it performs. The way we check this is by looking at forecasting error, or we will be calculating the forecast errors. The forecasting errors are the differences between the predicted values and the actual values, or the forecasted values and the actual values. And when we working with cross-sectional data, we often create 2 or 3 partitions. The training set is the largest part, and it's used to build the model, different models, and the validation test or set, which is used to evaluate those models so we can choose the best one. And we use another set called the test set, and sometimes it's called the holdout or evaluation set. And it's used to do the last check of the performance. And these partitions normally done randomly. In time series forecasting, it's just like the cross-sectional data. We need to avoid overfitting and test the model's predictive performance. But there is one big difference. With cross-sectional data, we can randomly divide the data set into training and validation sets, or in some books, they call them testing. So training versus testing. In time series, this doesn't work. Random splitting creates 2 problems. As we said, we have random splitting and non-random splitting. The random splitting creates 2 problems. First, it doesn't match the real forecasting situation. We always use the past and the present to predict the future. The other thing is it leaves gaps or holes in the time series, and many forecasting methods cannot handle missing values. So what we do instead, we partition by time. So, the partition cannot be done randomly. The earlier observations from the training set and the later observations are going to go for the validation or testing set. We're going to call them validation here. In some other books, they call them testing. We build the model on the training data and then test its forecasts against the validation data. And time plots that show both actual and predicted values in both periods are especially helpful in comparing models and spotting the weaknesses. So note that in the time series, we do not have the third set. Regardless of the name. So we have only 2 sets. Once we finish testing different models on the training and validation sets, we do not stop here. Before making actual forecasts for the future, we must join the training and validation sets back together into one full time series. Then we rerun the chosen model on this complete dataset. That model is the one we will use to forecast our future values. Why do we do this? Because there are 3 main advantages. Number 1, the validation period contains the most recent data, which is usually the most valuable for forecasting because it's closest to the period we want to predict. The second reason, by using the full data set, we give the model more information, which helps the model to be, or help uh, to be estimated more accurately. And the third one, if we only use the training set, we would be forced to make longer and more difficult forecasts. For example, if the validation set has 4 time points, forecasting the next observation from only the training set would require making a 5-step ahead forecast instead of just 1 step ahead. So that's why combining the partitions is such an important step in forecasting. The length of the validation period is not chosen at random. It depends on the forecasting goal, and that's why the forecasting goal is super important. So the data frequency is another thing, and how far into the future we want to forecast, which is called the, as we said, is the forecast horizon. The key principle is very simple. The validation period should mimic and imitate the forecast horizon. That way we can properly evaluate how the model performs for the type of forecast we plan to use it for. In Amtrak ridership case, if our goal is to forecast the next year, then the validation period should be at least 1 year long, so 12 months. If it's shorter than that, we won't be able to test how well the model works for longer or long-term forecasts. On the other hand, if we choose a validation period longer than a year, then our training set becomes smaller and the model will miss out on the most recent information available at the time of the prediction. So you have to be careful and you have to specify our goals. Sometimes we are tempted to use the most and kind of sophisticated forecasting methods, but we should always keep naive forecasts in mind. What is naive forecast? A naive forecast simply uses the most recent value of the series. And mathematically, if we are at time t, then the k-step ahead naive forecast is just the value of the series at time t. Very simple. And we're going to have an example when we move into R. For seasonal series, we can use what's called a seasonal naive forecast. In this case, we forecast using the most recent value from the same season. For example, if we want to forecast this December, we use the value from the last December and so on. If you would like to forecast on the coming October, then you use the exact value from the last October. So why are the naive forecasts important? First, they can be used directly. They're very simple, easy to understand, and sometimes they are accurate. And they're accurate enough for practical use. So sometimes there's no need actually to go for complicated stuff. And the second reason, and just as important as the first one, they serve as a baseline. So whenever we evaluate a more complex forecasting method, we should compare it against naive forecasts. So it's our baseline forecasting method. If the more advanced method does not clearly improve on the naive one, then it may not be worth that extra work, right? So just like other forecasts, we evaluate naive forecasts in the validation period, check the errors, and also create the prediction intervals, the one that we're going to talk about. Measuring the predictive accuracy. When our model is to measure predictive accuracy, we want to see how well the model predicts new values, not how well it just fits past data. That's why goodness of fit is not the same as predictive accuracy. Measures like R-squared or residual analysis show how well the model matches the training data, but they do not tell us much about predicting new cases. To measure predictive accuracy, we always use the validation period because those records were not used in building the model. Remember, we used training data to build the model. The forecast error at time t is just the difference between the actual value and the forecast value. Et equals 1 minus ft. Yt is the actual, ft is the forecasted one, right? From these errors, we calculate the accuracy measures. Accuracy measures, the common ones are mean absolute error, MAE. This one gives the average size of the error. And we have the average error, shows if we are over or under predict. Also, you have MAPE that give the error as percentages, and it makes it easier to compare across the data with different scales. And we have the RSE that penalizes the larger errors more strongly and has the same units as the data that we have. There is an important note here. If we compute these measures on the training period, in the training set, so that only tells us how closely the model fits the training data. And this is something this is the goodness of fit. This is not the predictive accuracy. To properly evaluate predictions, we must use the validation data or the validation period. Let's just go over these measures just quickly. So the first one is MAE, is the mean absolute error. The absolute value of the error, we just add all of them, then we divide by the number of the periods, right? And we have all of this. So on average, how big are the errors? And we ignore whether they're positive or negatives. So it's the average size of the errors or mistakes. Next one is the average error. This is the bias, and sometimes the error is going to be positive, sometimes going to be negative, right? So if you take the average and you got negative value, then the forecasts are too high. We are over predicting. Why? Because the forecasted value is greater than the actual. So F is greater than on average Y's, right? So the forecasts are too high. If it's positive, so that means we are too low, under predicting. And it tells you that the model is systematically underestimates or overestimates. Next measure is the mean absolute percentage error. And as we said, we just divide the error. Remember, there is Y minus F over the actual value. It's the percentages of the actual error, right? So on average, what percentage off are the forecasts, right? And this is the meaning of that one. So if, for example, MAPE is 5%, means forecasts are off by 5% on average. So we are looking for lower, all of these measures are looking for lower values, right? But we will have an issue if the YT is 0. If we divide by 0, we're going to have an issue here. That's why we are going to replace this measure by something else. MSE, which has, this one has the same unit as the data is, which is the square root of the mean error, right? So we take the error, we square it, we add the sum, then we divide by the number of periods. And then after that, we take the square root. So squares the error. So makes big error count more. So the meaning of this, this penalizes big mistakes or big error heavily. If your model sometimes makes very large errors, RMSE will reflect that more than the MAE. As we said, sometimes we will have the zero count. Sometimes we have zeros, right? And if you divide MAPE by zeros, we can have an issue. So if it includes zeros, MAPE run into trouble because it divides by the zeros. So if we have zeros, the calculation gives us an infinite result. So there are a few solutions to this. One is to exclude the zeros from values when computing MAPE, but this leaves out some information, and this information could be helpful or important. Another thing is to use other accuracy measure like MAE or MSE if they are appropriate, right? But there is another direct solution, which is the mean absolute scaled error, MASE, which is a scaled version of MAE that compares the model average error on the validation set to the average error of the naive forecast on the training set. So the validation MAE divided by the training AE of the naive forecasts. So the training set is used for the denominator to avoid the risk of hitting zeros, which is more likely with the fewer observations in the validation period. And the interpretation is very simple. If the MASE is less than 1, the model performs better than naive forecasts. If it's greater than 1, the model performs worse compared to the naive forecast. And MAPE gives heavier penalties to positive errors cases where the model overforecasts. MASE treats positive and negative errors equally. So that's one of the differences. That makes it more balanced measure. So in simple words, let's say, MASE tells you how wrong my model is on the validation set or period divided by how wrong naive on the training. That's why we compare this, what we are doing in our model, by what we got from the naive base model. So that's why if this is greater than 1, then this is worse than this guy. If it's less than 1, that means this guy is less than this. That means we are doing better than the naive base. So forecast accuracy versus profitability. So common accuracy measures like MAP or MSE, these are generally speaking considered pessimistic because they give heavier penalties to large errors. In real applications, predictive accuracy alone is not always the best performance measures. This is important again. Often we care about the cost of forecast errors, and these costs can be very different depending on the situation. For example, in demand forecasting, underestimating demand can have very different consequences compared to overestimating demands. And sometimes costs are treated equally in both directions. But in other cases, one type of error is much more costly. So costs can also be proportional to the size of the error again, or they might only matter beyond a certain threshold. So this leads us to an important point. Increased predictive accuracy does not always guarantee higher profitability, especially we're talking about businesses. So in financial markets, for example, profitability depends more on whether you get the direction right during extreme periods than on your overall accuracy. And a method that's no better than random most of the time can still be profitable, right? If it performs better than random during extreme events. I mean, we have an example here from the book. In 2009, we have an earthquake in Italy, and the scientists were accused of being too reassuring before the earthquake and faced serious legal consequences. But the opposite approach, which is issuing constant false alarms, also carries costs, such as, straining public resources and losing public trust. So this shows that the real measure we should often focus on is not just the accuracy measures, but also the profitability or the cost-based performance. So we need to look at both ways, the real consequences. When we evaluate the forecast, it's not enough to just look at the averages like SE or MAP. Forecast errors from methods like regression or smoothing techniques are often not normally distributed. This is something that we need to know. They may not be independent of each other, and they may not even be symmetric around the zeros, so they're not normally distributed, right? So that's why it's important to look at the distribution of the forecast errors. We have to look at the distribution. We want to see not only the typical errors, but also the extreme ones, the cases where the model drastically, let's say, under or over forecasts. To do this, we create time plots of the forecast errors or histograms of the forecast errors. So these plots help to understand the shape of the error distribution and the chance of getting errors of different sizes and directions, because if it's normal or not normal. For example, in some context, maybe like it preferred to have many small over predictions and only occasional large under predictions. And the last thing is, if the validation period contains missing values, we simply exclude those points when computing accuracy measures and when we plot the forecast error. So we just exclude these. The prediction intervals, as we did in statistics, is the range of values around a forecast that includes the uncertainty level. And this is more useful than just reporting a single number forecast point only, because it just tells us how much risk or variability we should expect. So suppose we forecast next month's sales as $50,000. That alone doesn't tell us how accurate it might be. So, but if we say that 95% prediction interval is between 40,000 and 52,000, then at least they'll tell us we are about 95% kind of, let's say, just in simple terms, we can say that 95% certain, we are certain that the actual value will be falling between that, within this range. Again, there's not the statistical term of being 95% certain. We have another definition. So notice that the point forecast is not always in the middle of the interval. This depends on the normality or no. Because if the forecast errors are normally distributed, prediction interval can be created easily, just like the regression. Just take the forecast and add and subtract few standard deviations before and after. In practice and in reality, forecast errors are not always normal. Most of the time are not normal, by the way. In the Amtrak ridership data, the errors from the error from the quadratic trend. We did not do this yet, but the Amtrak, it has a quadratic trend and it shows a skewed distribution. So in these cases, if the errors are not normally distributed, we can still build the prediction intervals using the actual error distribution from the training period. Like in a 95% prediction interval, we can be it can be constructed by taking the 2.5th and 97.5th percentile of the observed errors, not the 5. And this is, if we do 90% here, we take the 5 or the 5th percentile and the 95th percentiles of the forecasting errors. Yep. So these are, and we will see an example when we do the Amtrak, when we move into R. When we do partitioning, now we're speaking about the partitioning. We have two types of partitioning here. We will be doing kind of a type of a cross-validation, roll-forward validation, and the fixed one that we usually do. The fixed split let us evaluate only one step ahead forecast, or 1-2 step ahead, and so on. The roll-forward validation moves the split forward one period at a time, and that mimics real deployment, where we refit or refresh the model each period and produce the next forecast. In the monthly ridership example, we have 36 1 month ahead forecast, 35 2 month ahead forecast, 34 3 months ahead forecast, and so on. We get much richer evaluation of short horizon performance. If you look at this, we can do the first partitioning from January 1991 up to March 2001. This is my training data. Then we leave the validation period from April 2001 until March 2004. So we build the model here, right? So we train the model here, build it and train it. Then we validate the model into this period, right? Next partition, we take 1 month extra. So from January 1991 up to April 2001, this is my training period. Then we do validation period. We just move in one step ahead, and so on. We keep doing this. 36. We have 36 partitions, and every time we calculate the measures, right, and we compare them. So this is called a roll forward validation. It's very close to the concept of the cross validation, and again we are going to see this when we do the example. So let's jump in now to the example in R.